This is section 11.2, part D, chi-square test for two-way tables. Calculating the expected counts and then the chi-square statistic by hand is a bit time-consuming. As usual, technology saves time and gets the arithmetic right. So on your graphing calculator, if you want to do the chi-square test for a two-way table, you're going to enter your observed counts in matrix A. So to get to matrix A, you're going to hit second and then the inverse button, the x -1, which has matrix above it. And you're going to go over to edit and you're going to select matrix A. The dimensions will be a 3 by 3 matrix if it has 3 rows and 3 columns. And then you're just going to input your observed data. So if we go back to that wine and the types of music that was being played, we would input our data that is just on the inside of your table, not anything from the total. So you would input this part into your matrix. From there, you're going to specify the chi-square test and the matrix where the observed counts are found, and the matrix where the expected counts will be stored. So to do this, you're going to hit stat, and you're going to go over to test, and you're going to choose the chi-square test, and then we're going to adjust our settings. So our observed data is in matrix A. To do that, you would have to hit second, that x -1 to get the matrix, and you would just select matrix A. The expected is matrix matrix B. So again, you would hit second, hit the matrix button, and then just select the name of matrix B, and then you can calculate it. You can choose calculate or you can choose draw. You're going to get the answer on either one of them, and they're going to be the same. If you just hit calculate, it's just going to give you the numbers. And if you hit draw, it will show you the graph, and then it will give you the information. It will also tell you your degrees of freedom for that problem, the p-value, and the chi-square value. If you want to see what the expected counts were, you can go back to your home screen and you can go to that matrix and just select matrix B, hit enter, and it will display what the expected values were. So using that, let's do an example. Random digit dialing telephone surveys used to exclude cell phone numbers. If the opinions of people who have only cell phones differ from those who people who have landline service, the poll results may not represent the entire adult population. The Pew Research Center interviewed separate random samples of cell phone only and landline telephone uses who were less than 30 years old. Here's what the Pew survey found about how these people describe their political party affiliations. So we have Democrats or lean Democratic, refuse to lean either way, and we have Republican or lean Republican, and then people who have cell phone only and landline only. So this would be the information, not including the totals, that you would need to put into your matrix. So construct an appropriate graph to compare the distributions of political party affiliations for cell phone and landline use only. So because the sample sizes are different, we do need to compare the proportion of individuals in each political affiliation category in the two samples. The samples show the conditional distributions of political party affiliated for cell phone use and landline users. So they took the total for the cell phones, the 96, and they did 49 out of the 96 to get that 51% of them were Democrat. They did 15 out of 96 to get that 16% of them did not lean either direction, and the 32 out of 96 gave them that 33% were Republican. For landlines, they did the same thing, and they got those proportions. So if we graph this, you can graph this as a segmented bar graph. You can graph it as separate bar graphs. But if we did a segmented bar graph, we can see what percent is Democrat out of the 100, what part is not going to pick a side, and what part is Republican for cell phone and for landline users. Do these data provide convincing evidence the distribution of party affiliation differs in the cell phone only and landline user proportions? Carry out a significance test at the alpha equals 0.05 level. So we're going to have to do a 4-step problem. Remember, we start with the state, and in the state, you need to say your hypotheses and you need to give your significance level. So we want to perform a test of the null hypothesis is there's no difference in distribution of party affiliation in cell phone only and landline populations. And the alternative is that there is a difference in the population distribution, and we do need to state the alpha level, and our significance level for this would be 0.05. Next, we need to come up with our plan. You need to say what method you're going to use, and then you need to check your conditions. So we are going to use a chi-square test for homogeneity if the conditions are met. Now remember, when we're doing chi-square tests, the conditions you check are different than if we were doing a z-test or a t-test. So in these, we need to check random, large sample size, and independent. So the data come from a random sample of 96 cell phone-only users and 104 landline users. To check the large sample size, you first have to check the expected values. So you can put this into your calculator. Remember, you would just put this part without the totals into your matrix A. You would do the chi-square test, and you would store your expecteds into matrix B. And then you can pull those expected up. Just select matrix B, hit enter. It'll show you the expected values. And from that, we can see that all of them are at least 5, so the large sample size has been met. Next is we need to check independent. Because they are sampling without replacement, we have to check that 10% condition. So 10 times 96, we can assume in the country there's at least 960 cell phone only users under the age of 30. And if we do 10 times 104, we can assume there's at least 1,040 landline users who are under the age of 30. Next is where we're going to do the calculation part of this. So we can calculate this by hand, and remember, you do the observed minus the expected. So we would do 49 minus 46.08. You would square that, and then you're going to divide it by the expected, plus, then you would go to the next one, 47 minus 49.92, square that, divide by the expected, and add all that up. Remember, our degrees of freedom is the number of rows, which in this case is 3 minus 1, and times the number of columns minus 1. So 2 times 1 would give us 2 to get our p-value. Or if you just find it on the calculator, you're going to get a p-value of 0.20. So the last thing we need to do is write our conclusion on this. So because our p-value of 0.20 is greater than our alpha level of 0.05, we fail to reject the null hypothesis. There is not enough evidence to conclude that the distribution of party affiliation differs in cell phone only and landline user populations. So let's check our understanding. Canada has universal health care. The United States does not, but often offers more elaborate treatments to patients with access. How do the two systems compare in treating heart attacks? Researchers compared random samples of 2,600 U.S. and 400 Canadian heart attack patients. One key outcome was that patients' own assessment of their quality of life relative to what it had been before their heart attack. Here are the data for the patients who survived a year. Construct an appropriate graph to compare the distributions of opinion about quality of life among heart attack patients in Canada and the United States. So to do this, the first thing we'd have to do, since our sample sizes are different, is we're going to have to make these into proportions. So we're going to do the conditional distributions. Much better for Canada, we would do 75 out of the 311, and we would get that percent. Then for somewhat, we would do 71 out of the 311. We would do this for both Canada and the United States, and then we would graph that data. And our graphs would look like this. So in Canada, we got these percentages. In the US, we got these percentages for much better, somewhat better, about the same, somewhat worse, or much worse. Is there a significant difference between the two distributions of quality of life rating? Carry out an appropriate test at the alpha equals 0.01 level. So again, we're going to have to do a 4-step problem. Remember, in the state, you need to give your hypotheses and your significance level. So we want to perform a test of the null hypothesis is there is no difference in the distribution of quality of life in Canada and the United States. The alternative is there is a difference in the distribution of quality of life in Canada and the United States, and we're going to check this at the alpha equals 0.01 significance level. Next, for our plan, you need to state what method needs to be used, and then you need to check your conditions. So we're going to use a chi-square test for homogeneity if the conditions are satisfied. Next thing we need to do is check our conditions. So random, the data comes from separate random samples. Next is the large sample size. So remember, you have to check the expected counts. Again, you can do this on the calculator. You can do the chi-square goodness of fit. We can get our expected counts from the matrix B at that point. And we can see that all our expected counts are at least 5. So our large sample size has been met. Next, we need to check the independent. We clearly have less than 10% of all heart attack victims in the United States and in Canada, so the independent condition has also been met. Next is the due portion. Again, remember, you can do this by hand by doing the observed minus the expected squared divided by the expected. Do that for each part in the table and then add them all together to get a test statistic of 11.725. You would then find your degrees of freedom. Remember, it's the number of rows, which in this case is 5. And then you take the number of rows minus 1 times the number of columns minus 1. So 4 times 1 would give us a degrees of freedom of 4. If we find the p-value on the table, we would say what our p-value is going to fall between here and here. Or if we find the p-value on the calculator, we would get a p-value of 0.0195. Last thing we need to do is to write our conclusion. So since the p-value is greater than 0.01, we fail to reject the null hypothesis. There is not enough evidence to conclude there is a difference in the distribution of quality of life in Canada and the